This lesson is on the basics of hypothesis testing. Specifically, we're going to be looking at what comes before and after the calculations, because this is going to be the same regardless of which kind of hypothesis test we're talking about. And before we're done this course, we're going to cover a bunch of different kinds of hypothesis tests. In all of them, what we're trying to do is we're looking at a sample and we're seeing, do the numbers bear out what the claim says? So does the claim seem probable given the results of the sample, or does the sample seem probable given the results of the claim? You can look at it either way. So what we're going to be looking at in all of these is we're taking that sampling probability we looked at earlier and applying it to various sorts of claims. So the first thing we have in these formal hypothesis tests is a hypothesis. And we've got two kinds of hypothesis, and our claims can be either one. We can have what's called a null hypothesis, and that's a statement that involves some sort of equality. And when you're looking at your statement, you want to be thinking about what are those keywords that mean these things. So there's three ways we can have an equality. It can be equals, like the mean equals 12. It can be less than or equal, like the proportion is less than or equal to 17. Or it can be greater than or equal, like the standard deviation is greater than or equal to 42 centimeters. But they all have equals somewhere in there. So if you're thinking about what words would go along in these statements, equals often just is would be a keyword to look for. If we're talking about less than or equal, often it's something like at most. And greater than or equal is often something like at least. So those would be some keywords to look for when you see these sorts of questions. Alternate hypothesis, we'd be looking at things like is not. Or is different. Oops. If we're looking at greater than, well, obviously greater than could be some of our keywords, but things that tell us more, bigger, larger. And if we're looking at less than, pretty much the opposite to that. Less, fewer, smaller, etc. I actually strongly encourage you to keep yourself a list of keywords and add to it as you spot them in different questions, because they're going to look like a lot of different things, but these would be just some examples of words you might catch. So the claim itself can be either one of these things, and we do have to be careful with the wording, because depending on what the claim is, how we word our conclusion. So always when we do our calculations, the formal test is done against the null hypothesis. We're going to make a decision at the end, reject or do not reject that null hypothesis. That is not necessarily the claim, it may be the claim. So we're going to look at a couple examples and put them into symbols and decide which one they are. So if you've downloaded the version of the notes with blanks, you can be filling out the notes here. And again, trying these as you go along. I encourage you to try and do it that way. So looking at this first one, according to this pay scale, the average accountant in Calgary earns, and we're given an amount. So all we have in there for our keyword is earns. So earns is like is. This is the average amount. So we're looking at equality. So we do have that equal sign. So because the equal sign is there, this one is going to be a null hypothesis. Anytime we've got an equals anywhere in there, it's going to be a null hypothesis. Second one, we've got Encana has acquired more than 15 new well licenses per month. So that per in there tells us we're talking about an average. So when we put in our symbol, we do have to be thinking about what is this claim about. Right, the examples I put at the top, we had a mean, we had a proportion, we had a standard deviation. It can be about lots of different things. So this one, the per month is telling us it's about a mean. And our keyword telling us which symbol to use, more than. We need a greater than symbol. So greater than, there's no equality involved in more, right? It's not saying it could be 15, it's saying it's more than 15. So that one is an alternate hypothesis. And note with these hypotheses, we have different abbreviations. The null hypothesis is H with a subscript 0, and the alternate hypothesis is H with a subscript 1. Some people think of them as HI and HO, but it's actually 0 and 1. When you start having hi and ho, I always think you sound like you're one of the 7 dwarfs. And off to work we go. Next, at most 9% of rural water wells are affected by oil and gas drilling. So our keyword there, at most. But what is the claim about? Well, we've got a percentage here. So the percentage tells us we're talking about proportions. So at most is saying less than or equal to, right up here. That was even our keyword we talked about. So less than or equal to 9%, which we can put as that decimal value. And so we do have an equals in there. It's less than, but there's also equals when we say at most. It could be 9%, so then we would call that one the null hypothesis. So what we're ultimately trying to decide, is that null hypothesis true or false? Because this is based on a sample, there's always a chance we've made an error. And there's 2 types of errors, and it's important to consider both types, because each type of error always is going to have its own consequences involved. And some of those consequences are going to be big, and some of those consequences are going to be small. And you always want to look at, if you're setting up a hypothesis test, that you're doing the collection of the data and presenting this to someone, you want to minimize the type of error that's going to cause big consequences. And those big consequences could be your company gets sued, could be somebody dies. So the big consequences really do depend on this scenario. So the type 1 error, rejecting a true null hypothesis. So this is, you've done your data collection, your sample ends up being lopsided, the hypothesis was true, but for some reason your sample made it look like it was false. So that type of probability is alpha, and it's called the significance level. This is the same alpha we were using in the confidence intervals. So it's going to be the tails when we draw our diagrams. But it might only be one tail. We'll get to that in a moment. Type 2 is accepting a false null hypothesis. So this is, the null hypothesis is actually not true, but your data does not show that. So your sample, again, could be lopsided. So the probability of getting this false null hypothesis is also represented with a Greek letter, and this one's beta. And you may have seen those before, and you may recognize that when you put alpha together with beta, that's actually the first 2 letters of the Greek alphabet. That's where our word alphabet comes from. So these 2 values are inversely related to each other, meaning as the probability of a type 1 error goes up, the probability of a type 2 error goes down. So if the consequences are big for a type 1 error, you're going to say, oh, let's make alpha small and accept a larger beta. But if the probability of a type 2 error is huge, you're going to accept a bigger alpha in order to have a smaller beta. They're also both related to the sample size. The bigger your sample size, the less likely you are to make either one of those 2 errors. So large samples is pretty important. So some other terminology we have here, the test statistic and the critical region. So the test statistic is actually the value that comes from our sample that we use to make our decision. So there's various ways we can do test statistics. We're going to look at formulas in the next section, but for now, just it's the number that comes from your sample. The critical region is the values that would cause us to reject the null hypothesis. So if our test statistic falls in the critical region, that's when we reject the null hypothesis. So we have 3 possibilities for this critical region. We can have what's called a left-tailed critical region. That's the first picture. We can have a right-tailed critical region. That's our second picture. And we can have a 2-tailed critical region. That's our third picture. And they all depend on what's in our null hypothesis and our alternate hypothesis. So if our claim is greater than or equal to, we're looking at a left-tailed test. But also, if our claim is less than, we're looking at a left-tailed test. So notice these two are opposites of each other. So either one of those is going to tell us left-tailed test. Likewise, if our claim is less than or equal to or greater than, we're looking at this, the right-tailed test. And finally, if it's equals or does not equals, we're looking at the two-tailed test. So the null and alternate hypothesis always come hand in hand. They're always opposites of each other. So that when we're looking at that, if you're deciding, well, which one do I use to figure this out? I like to look at the alternate hypothesis. Because if you look at the alternate hypothesis, it acts like an arrow, right? When it's less than, it's pointing to the left side. When it's greater than, it's pointing to the right side. So that tells us where the tail is. And the does not equal is kind of like a double-headed arrow, if you want to think of it that way. So the critical region is that shaded region in the significance level, right? So our alpha is the shaded region. So as I mentioned earlier, if our test statistic is in the critical region, we reject the null hypothesis. So now we're going to take the question we had before, where we've got a claim, we're going to write it in symbolic form, we're going to identify those two hypotheses, and then we're going to say, is this left, right, or two-tailed? So still the same question with the accountant, right? So we said earlier that was the earns told us equals. So equals was our H0, our H1 is the opposite. So the opposite to equals is does not equal. And in our decision, is this left, right, or two-tailed? Remember, equals and does not equal gives us our two-tailed test. Second one are at most. So at most we said was less than or equal to. Less than or equal to is going to be our null hypothesis again. Our alternate is going to be the opposite, greater than, and we're going to end up with a right-tailed test. And I see I didn't highlight that answer. So all of this is what comes before our calculations. We can figure all this out without doing a single calculation. When we look at the whole hypothesis test, here's our steps. And we're actually going to jump to the end. So I'm going to go over the steps, but then we're going to jump to the last part. So we identify the claim, put it in symbolic form. We just did that. We figured the null and alternate hypotheses. We just did that too. Decide on alpha. So this is if you are creating your own survey, test, whatever it is, taking your own sample, figuring out your own alpha. Often on these questions, you're going to be given an alpha to use. Determine the test statistic. So this is the calculation part that we're going to get to later. Our critical values, critical region, more calculations we're going to look at a little bit later. And then we have two methods to decide our decision step. So method one is reject the null hypothesis if the test statistic is in the critical region. Do not reject if it is not in the critical region. So note that the nots go together, right? We do not reject when it's not in the region. So those totally go together with each other. Let's highlight that. So when we're doing that calculation, that comparison, we're always comparing two things that are the same. So we're either comparing two z values, two t values, two chi-squared, that's what this Greek letter here is, or two r values. So we're always comparing to the same thing to each other. So when we get to those calculations, that's one thing to keep in mind. But the other thing, keep in mind, the nots go together. So if we do not reject if it's not in the critical region, and we do reject if it is in the critical region. The other method, we reject the null hypothesis if the p-value is less than alpha. So p-value is another calculation we're going to look at in a little bit. Not quite yet. That'll be next lesson as well. So the last step, and we're going to jump to this, is writing a statement addressing the claim. So the wording of the conclusion is really important on these questions, and it's one of those things that's really easy to mess up. But again, it's completely logical. So work your way through the logic and you'll come to the right statement. And I'm going to point out there's 4 possible statements we can have. And 2 of these statements are what I refer to as strong statements. And 2 of these statements are what I refer to as weak statements. So the weak statements basically say there's not enough evidence. And sometimes there's reason to make a weak statement. There may not be enough evidence, and that's okay. So our hypothesis testing flowchart is just a little way we have here of looking at how can I word my answer. So we've already looked at the first part of the flowchart. Does the claim contain equality? So we either say yes and then the claim is H0, the null hypothesis, or we say no and the claim is H1, the alternate hypothesis. So we figured out how to go which way on that one. Our second one is that do we reject the null hypothesis? So is the test statistic in the critical region? Or if we're using the p-value, is p less than or equal to alpha? So if our answer to that is yes, that's when we get those strong statements, regardless of which direction we went for the first one. You'll notice again, this is the same question over here as we have over here. So we get that same strong statement on both of them, but they're not the same statement. They're both strong, but not the same statement. So the first one, if the claim contains equality and we reject the null hypothesis, we're rejecting the claim. So our conclusion, our strong conclusion says there is enough evidence to reject the claim. If, on the other hand, we've gone down this direction and we've said the claim is H1 and we're rejecting H0, well, if we're rejecting H0, we're supporting H1. So our strong statement says there is enough evidence to support the claim. Now, the ... dots that I put on here are really important because this is just the general form. If we want to actually use this, we're going to say whatever the claim is. So the ... dot's going to get replaced with some specific words. So if we're going the other direction and we say no, there's not enough evidence to reject H0, we're also making that weaker statement. So we're going to say there's not enough evidence to reject the claim in the case that our claim is H0, or we're going to say there's not enough evidence to support the claim. So those nots go together again. If it's not in the critical region, we do not reject H0 and there's not enough evidence. So keep those tied together. So question 3, we're going to look at these ones. Again, I encourage you to pause the video and try the questions as we get to each question, and then look at the answer. And if you want to watch the first one and then pause for the second one, that's okay too. So for each of these, we're going to look at the values that we're given. So we're given the calculations. We're not doing them at this point. And we're going to look at how to write that conclusion. So draw a normal curve showing the test statistic in the critical region, write the appropriate conclusion, and use the full sentence. So we have this claim, an engine oil is supposed to have a viscosity of, and we're given a particular amount, 25 measurements resulted in a test statistic and a critical value. And so if we look at this, the engine oil is, right, we've got that keyword again. That's telling us equality. So our claim is H0. It's also telling us that our claim is two-tailed, right? Because we have that equality. So if we take our diagram, right, we draw our nice normal curve, and we're going to put a line and shade in each region, get our two tails, and we're given this critical value is 2.064. So I label that as 2.064. Then I need to put my test statistic in the right place relative to the 2.064. And because I shaded the other side, these are always symmetrical. If we have two sides shaded, we know the other one's automatically just the opposite sign, but the same number. So if we look at our test statistic in this case, 1.756, that's going to be less than 2.064, so it's not in that shaded region. Right, so that's the one I've labeled in the green. We can see it's clearly not in the shaded region. So if our test statistic is not in the shaded region, let's take a look in our flowchart how we're going to answer this. So does the claim contain equality? We said yes, it's H0. Do we reject H0? Well, it's not in the critical region, so we're going to say no. So our conclusion has to follow this pattern. there's not enough evidence to reject the claim that, and then we can say the claim that's exactly in here. So steal the words right out of the question, that the engine oil has a viscosity of 735 MPa(s). So there is not enough evidence to reject the claim that the viscosity is 735. Okay, our next one. Time to assist a customer is less than 10 minutes. So we've got 125 measurements. We've got to end up with a test statistic of negative 2.955 and a critical value of negative 2.575. So, keywords here. Less than. Right, so we've got is less than. So less than, is that going to involve an equality? It is definitely not. So our first part of our flowchart, we're going to say no. Our claim is H1. What kind of tail are we going to have if it's less than? Well, that's H1 is pointing to our tail, so less than is a left tail. Didn't quite highlight enough there. So we look at our left tail diagram. Again, we put the critical value in first, so we see that critical value is the edge of our shaded region minus 2.575. We put our test statistic in next. Well, relative to 2.575, it's more to the left. It's even more negative. So this time it falls into our critical region. Quickly going to go back up to our flowchart. So we've said no, it's H1. Do we reject H0? Yes, it's in the critical region. So we're going to conclude there is enough evidence to support the claim that the time to assist a customer is less than 10 minutes. So the next lesson after this, we will be looking at the actual calculations. Where did this critical value come from? Where did this test statistic come from? And we'll look at both kinds that we might end up with, a T or a Z, and when we use which formulas. So that's it for this lesson, and you're ready to go on to the next one.